Good day, and welcome to the 2019 Jump into STEM webinar series. Jump into STEM is sponsored by the U.S. DOE's Office of Energy Efficiency and Renewable Energy's Building Technology Office, with support from Oak Ridge National Laboratory and the National Renewable Energy Laboratory. With Jump into STEM, our goals are to emphasize cultivating diversity of thought by underscoring the importance of interdisciplinary teams inclusive of women and minorities. The Jump into STEM program works with university and college professors from a variety of disciplines to support creative building science challenges that can be integrated with coursework curricula. Jump into STEM's network includes leveraging public-private partnerships with industry partners and STEM organizations to support the annual student challenges and events. With this slide, you can see a quick snapshot of how the Jump into STEM student competition works. Eligible students can compete for up to 4 paid internships at either Oak Ridge National Lab or the Renewable Energy Laboratory. You can go to jump.ideascale.com to view the eligibility requirements and the full schedule. When there, click on How It Works at the top of the home page to view a step-by-step process on the eligibility, building a team, ideation, and idea submission requirements. Also on the top navigation bar is the schedule for the Jump into STEM 2019-2020 competitions. Eligible students can participate in any of the 3 concurrent online challenges that are running right now through November 15th. These challenges are supported by an online webinar series designed to provide insights on industry practices, market issues, and other supporting resources to help student teams build and generate their idea solutions. Additionally, throughout the competition, Jump into STEM will host periodic Jump-a-thon events to spur innovation and creative thinking. After the 3 challenges close on November 15th, the Jump into STEM team will run a judging process to select finalists who will compete on January 31st, 2020 in a final event competition hosted at the National Renewable Energy Laboratory in Golden, Colorado. During this final event competition, judges will award the 2020 Jump into STEM internship winners. Again, please visit jump.ideascale.com for details on how it works, eligibility requirements, and the schedule updates. The first Jump into STEM challenge topic is focused on smart sensors and controls for residential buildings. Participating competitors interested in this challenge topic should develop a unique application that uses sensor data in residential buildings for the purposes of reducing energy, maintaining or improving occupant comfort, and/or to provide better responsiveness to the electric grid. Strong Ideas will present the proposed approach. They will identify sensor data and how the data will be used. The idea should also discuss the anticipated impact and a tech-to-market plan for this application. The second Jump into STEM challenge topic is to design a healthier and energy-efficient air distribution system for the small commercial building setting using your local climate zone. Strong Ideas will identify a novel system for the selected climate zone and will present implementation of the solution in a hypothetical or existing building. Solutions should articulate the expected impacts from the design system and also include a tech-to-market plan. The third Jump into STEM challenge topic is focused on pushing the envelope with innovative wall retrofit designs. Students are challenged to design a residential wall retrofit product or system that can address replacement or supplement of current leaky and unhealthy walls. Strong Ideas will identify how the wall retrofit will work and will be inclusive of details on how to address the issues of moisture and air tightness. Additionally, Idea Solutions should address one or more of the following issues: low indoor air quality, high energy costs, and/or high retrofit costs. Like other Jump into STEM challenge topics, this idea solution should include a tech-to-market plan. So if you have questions, please visit jump.ideascale.com, or you can email jump@ornl.gov. First in this series is a presentation on the market reality, the need for cost-effective wall retrofits by Gok Harris, a research engineer with the National Renewable Energy Laboratory. As part of the Building Energy Science Group, Chioke's research focuses on the application of fundamental heat transfer and material science principles to the development of novel, high-performance building components. He is also involved in the development of energy efficiency impact analysis software, including ResStock, a highly granular model of energy use in the residential building stock. Prior to joining NREL, Chioke was a AAAS fellow with the U.S. Department of Energy's Building Technology Office. In that role, Chioke co-created Scout, a software tool for evaluating the long-term energy and cost impacts of prospective building technologies, and supported the management of BTO's Windows and opaque envelope R&D portfolio. Chioke received his PhD in mechanical engineering from the University of Texas at Austin. Chioke also holds an MS and a BS in mechanical engineering from the University of Texas at Austin and Brown University, respectively. So please welcome Chioke Harris for our presentation.
Thanks for that introduction, Caroline. So today I'll be giving an introduction to the building envelope. In this presentation, I'll be going over some fundamentals about the building envelope and what it is, how the building envelope influences building energy use, and then some specifics, some comments about how the building envelope, the details, particularly of residential building envelopes, relate to the challenge that you have before you. So when you think about the building envelope, and if you'd advance the slide, when you think about the building envelope, it's really everything that you see. So it's all of the exterior features that you see when you look at a home, or you look at an apartment building, or you look at an office building. It's the masonry, it's the shingles or siding, it's the windows and the window frames, all of the trim that joins all of these pieces of the exterior envelope together. And it's also the interior side of that system. So the drywall and trim that finishes off the interior side of the envelope, and then everything that connects those two pieces together. All of that together comprises the building envelope. In this presentation, I may talk about windows and the opaque envelope, where I'm really just making the distinction between windows as sort of the transparent portion of the envelope, and the rest of the envelope as being the opaque portion, the part you can't see through. Next slide. So there are three main functions that are served by the building envelope. The first one is support, and that's the infrastructure required to actually enable the building to withstand both its own loads, the sort of weight of the structure and everything that's inside the building, the furniture, the building occupants, et cetera, as well as resist exterior loads, whether that's winds in particular, but also other loads that might include impacts from debris or other objects, particularly flying objects carried by the wind. So it's the whole infrastructure to support those physical loads. The next one is control, and that's the portion of the envelope that manages the environmental loads. So it's the part of the envelope that's serving to separate the interior environment or the indoor environment and the exterior environment. It's the thing that manages the flows of heat, air, and moisture between the interior and the exterior. It's the thing that tries to keep you warm inside or cool inside in the summer, in the winter or the summer, respectively. It's the thing that really enables the main function with respect to providing comfort inside the home. And then the final role, or the final function, is finish. It's the part that you actually see and experience. It's the siding, the windows and window frames, the trim, the roof material, all of those things that you see when you look at a home or you look at any other type of building. from the inside or the outside, that's the finished component. And it's, I think, often forgotten in discussions when you're talking particularly about building envelope energy performance, but it's actually a really key feature of the envelope because it's the thing that you see all the time, and it's the thing that people sort of appreciate. It's the thing that provides the architectural appeal of the building. So to dive in a little bit more on the control function, that's really the part of the building envelope that's most strongly related to energy use associated with the building envelope. So you can think of the building envelope, as I was saying before, as the element that separates the indoor environment, the place that you spend your time where you want to be comfortable, where there's conditioned air, cooled or heated to provide thermal comfort, and the exterior environment, whether that's protection from hot or cold air, humidity in hot, humid climates in particular, solar radiation that includes visible light when you want to be in the shade, as well as ultraviolet and near-infrared light, wind, and also what the wind can bring with it, particularly rain and snow, so driving, protecting you from driving rain, driving snow, and then also contaminants that may be airborne, whether that's volatile organic compounds or VOCs, particulate matter, other sort of environmental airborne pollutants that are things that you don't want to be breathing or interacting with. When we drill down into how that actually plays out in terms of how the building envelope affects energy use, just to start, to give a little bit of context, on the left, that figure, that bar plot shows the contribution to total US primary or source energy use that comes from buildings. It's the column on the left with residential on the bottom and commercial stacked on top. Together, residential and commercial buildings make up more total US energy use, and this is 2018 data, than the industrial sector or the transportation sector. So it's a major contributor to US energy use. If you think about it, usually US energy use in a given year is around 100 quads, 100 quadrillion BTUs or British thermal units. And so 20 quads coming from the residential sector, it's about 20% of total US energy use. Moving to the middle figure, we can break that energy use out by end use. So all the different appliances that are in a home and the different functions that come from the heating and cooling system. And the bars that are darker represent the energy use that's associated with the building envelope. So heating and cooling, as I mentioned before, that's the indoor environment that you're trying to maintain against the elements that are going on outside the building. So the heating and cooling system, and then fans and pumps, which is the ventilation fans, the water pumps, and other systems that are used in conjunction with the heating and cooling system to distribute that hot and cold service around the building, together comprise that energy use. Moving on to the right figure, we can break that down further into the various components of the building envelope and how those actually stack up to be the total energy use that's coming for heating and cooling. So in the cooling season, there are a couple of dominant players, particularly solar heat gain through windows. So when the sun is shining and it's very hot outside, if you have a cooling system in particular, an air conditioning system, the solar heat gain, the sun that's coming in through the windows, is heating up the interior environment. So you're having to use your air conditioning system to cool off the interior space, counteracting that, that additional energy coming from solar radiation. In the wintertime, in the heating season, you're losing heat through every component, essentially, of the envelope, whether it's the opaque envelope shown in red, through the roof, through the walls, and out through the foundation, as well as losses associated with infiltration. And I'll talk a lot about that a little bit more later, and how that actually stacks up in terms of contributing to energy use, as well as through conduction, particularly in the window frames. So you'll see that if you've ever touched a window frame, particularly in an older home or in a home with metal frame windows, those frames are often very cold to the touch, and that's a major source of energy use coming from windows in the wintertime. All of this energy use that's associated with the building envelope is associated or is coming from heat and mass transfer. Both heat and mass transfer move energy along spatial gradients from high concentration areas or high intensity areas to lower concentration or intensity areas. So in the case of heat transfer, that's moving that energy from hot areas to colder areas. And in the case of mass transfer, in the context of the envelope, we're particularly thinking about water vapor or humidity. And so that water vapor is moving from a high vapor pressure area to a lower vapor pressure area spontaneously. Going back to thinking about heat transfer, there's three primary modes or mechanisms by which heat is transferred. These are all probably familiar to you, but just to illustrate them, conduction is the mechanism by which heat is transferred through direct contact between two materials. So an example would be an electric cooktop where you have a pot sitting on the burner element. And then when that burner element is turned on and heats the pot, it's heating the pot through direct contact between the burner and the bottom of the pot. Convection is heat transfer through air movement. And so you might turn on a ceiling fan in your bedroom on a hot day to help feel cooler. The air movement across your skin is convection that's helping you feel cooler and sort of giving you the impression that the space is cooler than it is. Convection is also used usually when you're using a fan associated with some heat source. That's taking advantage of convection, taking advantage of air movement to improve or otherwise change heat transfer. And then radiation is heat transfer that occurs without direct contact or necessarily without air movement. So the most common example would be something like you're standing by a campfire. You can often feel the heat from that, particularly if it's quite large. You can often feel the heat from the campfire even when you're standing quite rather far away from it. And you might even be able to tell, you might be able to perceive on your skin that the air around you isn't that warm, but you can still feel that heat. That's heat transfer through radiation. So if we think about what that actually looks like, we can visualize the effects of heat and mass transfer using infrared imaging. So looking at the image on the left first, this is a series of townhomes or row homes. And the home that's in the center of the figure, or the center of this IR image, has had its windows retrofitted. So in this figure, darker colors, dark blue colors, represent colder areas. That's why the sky that you see above the homes or the plants around the home are very dark. They're essentially the color or the temperature of the surrounding air. So for that building, that home in the middle, because they've replaced their windows with some high efficiency, high performance windows, you can see that those windows are relatively dark. That means that the heat that's inside that home on this cold day, presumably a winter or late fall day, is not being transferred through the window and to the outside. Conversely, the home next to it, which you can tell kind of from the shapes in the image, is a similar home, was built at the same time, probably has either its original windows or certainly windows that are quite old and don't perform as well. And so you can see all of these windows are very bright in color. They're sort of yellows, reds, and even white, which is sort of the hottest temperature in the range in this figure. And so that's showing that a lot of the heat that's inside the home is being lost through the windows. And in fact, so much heat is being lost through the windows, you can see above a lot of the windows, there's actually additional heating of the facade around that. That could be either the heat loss through the windows, or it could also be poor air sealing around the windows, or otherwise poor sort of joining between and sealing between the window frame and the building itself that's leading to additional air leaking out around the window. One thing that I think is sort of interesting about this figure is that you can see both homes appear to have very similar entry doors. So it seems like in the home that was retrofitted, they maintained the entry doors perhaps for historical preservation purposes or because of appearance, appeal, sort of the appeal of the way that the doors looked. But you can see that the glazing in those doors doesn't perform very well because it hasn't been replaced. On the right side of the figure, you can see, or the right side of the slide, you can see the skyscraper. That's the Aqua Tower in Chicago. And it has these sort of undulating shapes that are created by having each floor of the building have a slightly different outline. And so they can create this kind of wave pattern across the facade. But what that actually translates to, if you look to the left of the visual picture, looking at the IR image of that building, what happens is because those floor plates for each level are actually connected through from the interior to the exterior of the building. On a cold day, all the heat in that building gets transferred through the floors and out to the outside surroundings. And essentially, the building starts to act sort of like a radiator, heating up the surrounding air because the floors are these sort of conduction conduits to the outside. On the bottom right of the slide, you can see two figures. The first one on the left is showing an interior space in a home where the drywall has been removed and spray foam has been sprayed into the spaces between the vertical studs. Spray foam in general provides both insulation as well as some air sealing because it's very dense and it sort of adheres to all the surfaces that it's sprayed to. So it can perform very well, but you can see in the IR image, there's still this sort of purple boundary, which is where cold air is coming into the interior space. Well, how is that happening? It's happening because even though the spray foam is sealing each individual cavity, at the joints between the walls, between the two side walls, and at the joints between the floor and the wall and the roof, or the wall and the ceiling structure, air is still able to get around that. And so you have air leakage that's coming, cold outside air that's coming through. So even though you spent all this time and effort putting all this spray foam in, you're still losing energy that's coming in as a result of air infiltration. There are more consequences to improper management or inadequate management of heat and mass transfer besides just feeling cold, having cold air come in, or feeling uncomfortable and chilly when you stand next to a window or when you sit next to a wall. On the left side, there are a bunch of images that show essentially what happens if you don't properly manage moisture and the resulting decay that can occur when you have moisture, particularly condensation, inside a wall, and the resulting failures that can happen. Where you have mold growth, you can have delamination of structures, decay of wood, and structural problems as well. On the right side is a picture of an aluminum framed window. And what's happening is there's condensation forming on the frame, on the inside side of the frame. And that's happening because this picture was taken in the wintertime. And because aluminum is a very good conductor of heat, and it's very cold outside, that cold air outside is cooling the window frame. It's making the window frame quite cold, actually. And since in the wintertime, usually humidity is higher indoors than it is outdoors, that humid, or relatively speaking, that humid air is reaching the window frame and then cooling off and not able to sustain as much humidity in the air at a lower temperature. That results in condensation on the surface. And then usually when you have something like this, you'll end up with that condensation kind of accumulating and then pooling and running down the frame to the sill, where often you'll get a puddle. And over time, that puddle of water that's forming every day, every winter, you'll eventually get decay or rot or mold around the base of the window frame that's arising as a result of this unmanaged water or moisture that's in the envelope. So when you're not managing moisture and you're not managing heat very effectively, it can have consequences not only for the structure and sort of physical performance of the building and sort of keeping decay at bay, it can also make people feel unwell. So sick building syndrome is a well-documented problem that occurs when indoor air quality is negatively affected as a result of inadequate control of some of the contaminants that are inside a building. So when you think about a building, particularly when you've built a very high performance building, you've done a really great job of insulating, sealing out the outside air, preventing infiltration, and you've developed this phenomenal high performance building. And then you say, well, great, now we have very small, we don't need very much heating or cooling because we've kept out all the unwanted hot or sort of heat losses that are coming from the outside. So now we have a downsized heating and cooling system. or we don't run it as often, or we don't have as much ventilation. And so all of the things that are in the building that maybe normally would have left through infiltration sort of naturally, leaking out through the facade, or being transmitted, being circulated as a result of constant operation or more regular operation of a much larger heating and cooling system, those are now staying inside the building much longer. And so you can have consequences for the health and safety of the building occupants as a result. There are a wide range of contaminants in buildings that can lead to indoor air quality problems. As some examples, you can have ozone. Ozone is not as much of a problem typically in residential buildings as in commercial buildings. The major driver of ozone generation is often laser printers and copiers. And it has a sort of distinctive smell that if you've ever spent a lot of time in like a Kinko's or a copy center, or any room that has a lot of copiers operating in or a lot of printers operating in, you can kind of smell, you kind of know what that smell is like. That can accumulate in buildings, particularly if you don't have good management of your airflows. You can also have accumulation of volatile organic compounds or VOCs. Those can come from paints and solvents. They can also come from synthetic furniture or fabrics and treatments that are applied, like chemical treatments that are applied to those. So like flame retardants applied to upholstered furniture, for example. You can also have, you often will have moisture sources. This is particularly true in some types of commercial buildings and also in residential buildings where you're doing, if you're cooking, if you're boiling water, that steam that's coming off your pot of boiling water, that steam is going into the air as water vapor, and then becomes a moisture source in the building. Also, anytime you take a shower, a hot shower, the steam that's coming off of your shower is also going to be moisture, additional moisture that you're adding to that indoor environment that you're going to have to manage somehow. Radon is a challenge that depends a lot on where you're located, and something to think about, getting some information about the particular area that you're in and whether or not radon is a challenge there. Radon is a naturally occurring radioactive odorless and colorless gas that comes from, I think, certain types of geologic formations. And it just sort of percolates up from underground, and it can get trapped in your building if it comes up through the crawl space or foundation or basement, and then it can sort of get stuck inside your building. And it's not great to be exposed to high concentrations of radon for long periods of time. You can also have particulate matter sources, particularly if you have combustion inside your home. So if you have like a gas range or a gas cooktop, or your water heater, if you have a natural gas water heater, and that's inside the conditioned space of the home versus in the garage or in some sort of like exterior kind of utility shed. But anytime you have any combustion, particulate matter can be a challenge. And then finally, you can have CO2, high concentration of CO2. The particulate matter, or sort of like the combustion and the CO2 levels, can often go hand in hand. If you have, again, any of these combustion sources, you're consuming oxygen in that combustion process, you're replacing it with CO2, or some of it with CO2. And so you can end up with very high CO2 concentrations if you're not bringing in new sources of oxygen from the outside. So when you think about these things, it's really important to keep in mind, these are all things that are sort of natural, they're not all naturally occurring, but they're all things that you can control to some extent, but you can't control 100%. So radon is something that's naturally occurring. VOCs, you can do a lot to control the sources of VOCs by choosing lower VOC content products. But then like moisture sources, people are going to take showers, they're going to cook, and you're not going to be able to tell them, well, now that this home has been improved, you need to not cook so much. That's not really going to work in terms of providing an occupant with a home that they want to live in the way they're going to live in it. And the figure shown on this slide just kind of illustrates this point that if you have an envelope that performs in a way that is not managed properly, in this case, you can end up with a lot of mold formation. So that's sort of mold forming on the ceiling, or kind of the ceiling and wall joint. Obviously, that's not something that you want to have in your home, and that can occur for a variety of reasons. It can occur because of a water leak inside the walls or ceiling that's making the drywall wet and saturated. And then particularly if you have sort of this wet, saturated drywall, and it's also very hot, you can end up with an environment that's sort of the perfect breeding ground for mold and decay. So in new buildings and new homes, there are a lot of different materials that can be used to reduce energy use. Those range from, in this case, various types of insulation materials. The higher performance materials will have a higher R value. So as an example, a fiberglass bat, and it's usually R value, given as R value per inch of thickness of the material. And so you might have a fiberglass bat that's 2 inches thick and is maybe R4 or R5, and that can go all the way up to a vacuum insulated panel, which might have an R value of R25 to 40 per inch. So higher numbers are better, and there's sort of a range of materials in between. All of these materials have advantages and disadvantages in terms of cost, material safety, time of application. Cellulose is often, well, cellulose in particular is often a little bit damp when it's applied. That's how you get it to sort of stand up in these cavities, even though it's blown in as a kind of loose material. And so that has to dry out, and that can create some challenges depending on your sort of construction timeline and approach. So they all have advantages and disadvantages. This is not an exhaustive list or either. It's just sort of to illustrate the point that you can have kind of a range of materials that perform differently and have different attributes depending, and that different ones can be appropriate depending on your desired application. In your envelope, you'll also be employing in a new building, you'll have some types of air and vapor control strategies, control layers. So in this picture, the black material that's shown kind of in the upper left of this picture is a vapor barrier material that's then been actually, each panel of the material, each piece of the material is then sealed around the seams to create a sort of continuous layer all the way around the envelope of vapor control. And then the insulation, which is this foil-faced material that you're seeing in the areas that aren't black, that material has then been taped off. So the blue strip or blue strips that you can see is between each panel of rigid insulation on this building. They've then taped the joints. So since the rigid panel, the rigid foam panel is more or less impermeable, has very low permeance, particularly with the foil facing on it, then when you tape those joints, you create a very tight seal. The positioning of these layers of vapor control and air control, airflow control, are important to keep in mind because they are climate specific and they're specific to the configuration of the building that you're looking at. And so you need to be sensitive to, and I'll talk about this a little bit more later, you need to be sensitive to where those layers are placed depending on the climate of the home that you're retrofitting. If you're in a hot, humid climate, the way you position the insulation, the layers of insulation, the layer that controls the vapor transport, and so on and so forth, may be different than in a cold climate or in a sort of temperate marine climate. Then finally, for windows, you can do a lot of different things with windows. The sort of good news story about windows is that they come as a package. And so you don't usually have to do a lot to the window itself. Once it's sort of delivered to the site for construction, the windows can incorporate a lot of different features to improve performance. They can use low thermal conductivity frame materials. So wood and vinyl in general tend to be less thermally conductive than materials like aluminum, although you can find aluminum frame windows that are relatively high performance that use relatively advanced materials as the thermal break, and that thermal break essentially separates the aluminum on the outside that's exposed to the cold winter air or warm summer air and the aluminum that's on the inside. So it reduces heat transfer between those two sides of the window and helps prevent what you saw earlier in terms of condensation formation in the wintertime. You can also get what are called IGUs, or insulating glazing units. That's the glass that goes inside the window frame. You can get both double and triple pane IGUs. And then with each sort of additional layer of glass, you'll get improved performance, reduced, a lower U factor for the window overall. You can also, those windows will often have at least one, if not two or three, low E coatings or low emissivity coatings. Those coatings can also further reduce the U factor of the window overall. There are other things that can be done, for example, with the spacer between the two panes of glass or three panes of glass, as well as inserts that can be put into the frame structure and the design of the sort of cross section of the frame as shown in this picture with the cutaway. Depending on how that frame structure is actually designed, the inside of that frame can also help reduce conduction heat losses through the frame beyond just using a material that's lower thermal conductivity. So you can do a lot of different things, or the window manufacturer can do a lot of different things to kind of lower the U factor of the window to help reduce heat transfer and improve performance. For existing buildings, there are some different ways to improve performance, but it's often a complex and expensive proposition. So this home shows, this home is a home in Atlanta that was built in the 1920s, and as part of a retrofit pilot project to improve the air sealing and insulation performance of that home, what they essentially did was they removed the existing exterior finish layer, kind of the exterior cladding all around the home, and then sprayed in cellulose insulation that they then covered with an air barrier material or a vapor barrier material, and then kind of reassembled the exterior finish layers on top of that. So there was a lot of not only the labor to actually install the new insulation, the new vapor barrier layers, but also all of the tear down to remove the old exterior and put up a new exterior. Ended up being a lot of labor to kind of get all of that to happen, even on a relatively small home. So when we think about retrofit solutions, it's important to keep in mind that not only do they need to be high performance and cost effective for the customer, for the homeowner, they also need to be desirable. They need to be appealing, particularly visually appealing, and they need to be a low effort, a low commitment process to actually get them installed in the home. So this picture shows some homes in the Netherlands, a row of homes, and these homes have all been retrofitted with rooftop solar, a high performance, a highly insulating roof structure, and highly insulating windows and new overcladding that improves the R value, the overall R value of the walls. But the challenge here is for them to do that, they relied in part to bring down the cost. They relied on the fact that all of these homes have exactly the same shape. And so it was easy for them to develop a solution that they could then repeat over and over and over again. When you think about any type of retrofit or remodel that a homeowner might undertake, it's important to keep in mind that you want to really lower the barriers to entry and make it something that they want to have as much as possible, as opposed to simply making it an economic decision where they're saying, oh, well, it pays back, you know, it saves me money on my energy bills and it pays back in X number of years. That's certainly an argument that's compelling to some homeowners, but you'll get more homeowners engaged and interested if it's something that is easy for them to adopt and is something that they want to have. You can see that with rooftop solar. A lot of the companies that have started up in the past 10 to 20 years to provide rooftop solar or rooftop PV for residential customers, they've really done a lot of work to reduce the barriers to getting solar onto someone's home. So that the number of times they have contact with the customer, or essentially you come in, you sort of give your sales pitch. If they say yes, that's it, and then you're off to the races. There's no effort, really, there's very minimal effort for the homeowner to make that, to get solar on their roof. And that's been a key, getting rid of all of these intermediate steps, or streamlining all these intermediate steps, whether it's permitting, site inspection, assessment, and system sizing. All of these intermediate steps are all taken care of. It's all one provider. And all you have to do is sort of sign on the dotted line once, and they take care of everything for you. So it's not just a question of developing something that is has good performance, but also thinking about the business model and the approach to the market is important as well. So this row of homes kind of gives an example of a case where, in fact, you could take an approach somewhat like what was done on the previous, what was shown on the previous slide in the Netherlands, where there are multiple homes with very similar form factors, very similar shapes and facades, that you could develop some sort of retrofit solution, and you could repeat it, kind of tile it over multiple buildings. And so you could kind of amortize your costs and your investment such that you could really do a lot to drive out cost for the homeowner by kind of systematizing things. So if you go to the next slide, that's not what most residential streets in the US look like. They look more like this, where every single home has a different shape, a different size, a different number of stories, different materials that they were built with, built at different times, different number of retrofits or modifications that have occurred since they were initially built, different states of repair, or you know, they're in sort of different shape. And so all of those factors come into play when you're thinking about making a retrofit on a residential building, on a single family home. You need to kind of be sensitive to and cognizant of all those different factors that can influence influence whether or not your solution is going to be effective and how much it's going to cost to install. So I want to use this image of a home as an example of perhaps a home that was built around the era that's relevant for this particular challenge. And on its face, I selected this home in part because on its face, sort of looking at it from the street, it seems like a home that has a relatively simple structure. It's sort of kind of a one-story box joined to a two-story box. And so thinking about the actual process of developing a retrofit for this home, you think like, oh, well, that's relatively straightforward. It's kind of just two boxes, and you kind of just make a wrapper for two boxes and you're done. But if you go to the next slide, there's a lot of details to this shape that start to add complexity, even though on its face it might seem fairly straightforward. So you have the fact that you have interfaces kind of moving from left to right. You have actually two different depths. You have kind of a step out from the first story to the second story. You have this overhang that's over the front door, and you have to kind of work your retrofit around the fact that there's this small kind of roof structure around the overhang for the front door. There's then a step out from the two-story box to the one-story box. There's a step out in the facade. So you have to work around that detail element. You have to wrap around the sloping roof that joins from the first story roof into the side of the second story portion of the home. You also have to work around all of the window features, the window frames and sills, and kind of properly join together the envelope at those points. And you also have to do the same around the garage door and around the front door. And in fact, actually, I would emphasize that part in particular. The joining around where the windows and doors are located is particularly important, because since you have changes in the depth of the facade, you'll have to manage the way rain and wind-driven rain flow, because what you want to be particularly careful of is that you don't end up with a situation, for example, where rain hits the window, runs down the window pane, down the frame, down the sill, the exterior sill, and then pours into the inside of a retrofit, where it's pouring all over the materials that you've put into some kind of overcladding or recladding, it's really important that that rain actually flow out to the exterior and onto the ground outside the home instead of inside the wall retrofit that you've put together. The other thing I want to point out with this small image at the bottom is you have to keep in mind, you have to work around penetrations in the wall as well. So this is a picture of a home that's under construction, but you can see where they've had to cut holes in the exterior insulation to accommodate vents and wiring and other things that are going from the inside to the outside of the house. And you'll have to do the same. There'll almost certainly be an electric meter, there may be a gas meter, there may be drains for or vents for like a clothes dryer. You may have vents for a bathroom fan or other ventilation fans. You may have penetrations for a cable box or telephone service that go through the first floor in particular, but the first floor exterior facade. And so you have to work your way around all of those penetrations. You can't kind of just like paper them over with some sort of retrofit. You have to be able to accommodate those features on the outside of the building. So I wanted to give some kind of closing thoughts about the challenge and things that you should keep in mind when you're putting together your proposal or your solution. I would say to the discussion I was just having, think creatively about dealing with interfaces. There are a lot of them, even in a relatively simple building, but they're very important to get right. Strategies that you can use to reduce the complexity and the labor effort and the risk of error around those interfaces, I think are really something to think about. Maybe it means using laser line scanning or other scanning systems to automate the production of a window frame surround so that you know that it's dimensioned correctly, or using a drone mounted imaging system to collect data about the exterior facade. Maybe it's using additive manufacturing to assemble custom inserts or custom fittings and trim pieces to help bridge the gap between the retrofit components that you're proposing to put on the envelope and any existing components that you're leaving in place. Be careful as you're putting this together to areas where you might be introducing thermal bridging or air leakage inadvertently. As I pointed out on one of the earlier images, it can be easy even when you think you've sort of covered everything, you've done your due diligence on putting together a system that is airtight, you might have ended up with a space where you still have air leakage. And so thinking about what areas or what components can lead to air leakage and how you're going to effectively address those. And the same thing goes for thermal bridging as well, where you maybe use a particular type of connector that's then becoming this conduction pathway, sort of like what I showed with the Aqua Tower, where you're conducting heat from the interior to the exterior inadvertently because you've connected those two together with some high thermal conductivity material. Keep in mind that if you're going to put something on top of the existing facade, you have to be aware of the performance of that existing facade. If it's highly vapor permeable, you'll need to keep that in mind when you specify the materials that go into the various layers of your retrofit solution. You should also understand the implications of climate, as I mentioned before, on the vapor and air management layers and where they should go inside the envelope system for the retrofit. You should make sure that you're aware of what the guidelines are for doing that placement, and those guidelines are kind of well established. And so you don't need to necessarily reinvent the wheel. You can kind of build off of established research that's figured out how to position those various air and moisture materials, control materials, to get good performance. And then finally, think about if there are any ways that you can incorporate multifunctionality. And what that means is the envelope has those sort of three major functions, but that doesn't necessarily mean that that's all the envelope can do. That's just what all the envelope does typically today. It's not inconceivable that you could incorporate sensors or actuators or movable elements that are automatically controlled, or even potentially some ventilation system, or even a heating or cooling system that's somehow integrated into the envelope that provides some kind of benefit and some kind of energy savings because you're able to put that inside an integrated package. So think about ways that you might be able to incorporate multifunctionality to get additional benefits that you wouldn't get from a sort of traditional envelope system or traditional envelope retrofit. And then finally, I wanted to, as we transition over to questions, these are some resources that you can use to get a feel for kind of what are the best practices and best strategies for handling envelope retrofit design, material selection, dealing with air infiltration, dealing with indoor air quality. All of these things can kind of help you learn more about all those things that you need to keep in mind as you're developing your proposed solution.
Why don't I ask you one of these questions that came in? I think we have time for one. Can you share any information on existing solutions? For instance, what are homeowners doing right now? Could that be kind of a way to jumpstart some ideas about what to respond with for this challenge?
Sure. There's a couple of approaches that homeowners I think are using now. One is often called drill and fill, and that's blowing usually cellulose, but sometimes a particular formulation of spray foam into the cavities in the stud cavities in the building envelope, in the walls. And that can be done by just, usually the holes they have to drill are just a couple inches in diameter. They can just patch the drywall on the inside of the building afterward. That doesn't work in all climates because you are adding a bunch of insulation, but you're not necessarily adding air sealing or vapor control at the right layer. And so you have to be kind of cognizant of that. And that's not appropriate for all climates and for all homes. The other thing that you can do is there are some insulated siding options. So if you're doing like a vinyl siding refit, you're getting new vinyl siding, you can get siding that does have some a thin layer of insulation attached to the back of the siding, and so as they're putting up the siding, the insulation sort of comes with it. That is limited by the fact that the insulation they're using is relatively thin, so you don't get a big boost in your R value. But it does mean that if you're already planning on doing a siding retrofit, you at least are sort of taking advantage of that opportunity to kind of get a little bit of additional insulation, a little bit of additional benefit at the same time, without a lot of extra labor cost associated with that. Those are the two big ones. Most anything else requires sort of what I showed before, where it ends up being a lot of tear down and kind of reconstruction of the envelope. The other big thing that people often do is they just do their windows, because the windows are kind of already in openings in the facade. Oftentimes, if they want to improve, if a homeowner wants to improve performance, they may just choose to replace the windows or do some kind of get insulating drapes or something like that to try, or maybe like some other type of exterior or interior kind of retrofit that's applied to the windows to try and improve performance that way.